Hello, good morning, everyone. Today, inshallah, we will go through the phases and how to do generating set for a certain subvector space. This is really a very important session. It's going to be lengthy one. We will go through phases, spans, and vectors. Of course, it's a part of the vector space. We are in linear algebra with programming, and I am Omar Muhammad Salah, as you know. I will start with a summary of the previous session. As I told you, this session is going to be a little bit long because I want to do first a summary about the stuff that we talked before in the previous two sessions. Then, I will do the part of the phases, or we will go through the theories and the propositions of phases. Then, and finally, we will do some exercises together. I need you to sit tight, bring your paper and pen, and once you start, or when you are listening to this record, I want you to feel free just to stop, write or resolve the problems and redo it again. This is the way to have the best outcome from this lecture. I will start with the beginning of a vector space, and we already had this previously in the previous session. Once more, for all of you, I know some of you, they are usually confused about vector space. Vector space is a collection. It's a non-empty set of a bunch of vectors whose elements are who consists of vectors or objects. Uh, we have just only two operations are closed in vector spaces. The first of them is the closure of the addition property and the closure of the multiplication by scalar property. How it is written, we already, once more, we did go through this previously. For every u and v and w, and those are vectors, belongs to the set of vector v, and for every a and b, let me get my laser pointer, and for every a and b belongs to r, so I have two things I've defined at the time being. The first is the set of vectors, which are u, v, and w. And the second are the constants, which are numbers, and they are real numbers, belongs to the set of all real numbers. And under or after this definition, the following properties hold. Number one, the additive closure, which means if you have two vectors u and v and you add them together, the result will be also belongs to the main set of the vector space V. So imagine, for example, 1, 1, 2, 2. If I add them together, they will be 3, 3, and 3 and 3. And also it is a set, or it is a vector belongs to R2. So that's an additive closure. Of course, the additivity, associability, the commutativity of the addition of the vectors, and it's all making sense because you are talking about the addition process, the existence of the zero vector, which is the identity for addition, v plus 0 is going to be v, and the existence of the symmetric, or the negation, or the inverse, or the reverse of a vector. All of these are names for the same vector. Bottom line, if you have, for example, 1 and 1, then you should have -1 and the -1. If you have 2 and 3, you should have -2 and the -3. Once you add them together, you will get the 0 of this vector space. So, bottom line, we are talking about enormous number of vectors that when you add them together, the result will exist. That when you multiply, the result will exist. The other 5 properties are all related to the scalar multiplication. So for example, if I have 1 and 1 and multiplied by 10, I will have the vector 10 and 10. And still, it's one of the vectors of R2. Also, if I have ABV, it's exactly like having AB then multiplying by V. Also, we can have the distributivity of vectors, which is a constant and they can't distribute it on U and V. Also, for the addition of the distribution of the scalars on certain vectors. So if I have A plus B times V, then I equal to A times V plus B times V. The existence of the identity of the multiplication of a vector. So 1 times V, it's equal to V, as you can see. So those are the 10 properties related to both the addition and the multiplication by scalar. And those are the conditions of a vector space. It is really very simple. So once more, when we go to subvector spaces, same conditions apply, because every subvector space from a vector space, it's by itself, it's a vector space. The definition goes like this. Let V be a vector space. So it's a huge set. And inside this huge set, there is a smaller set, which is W. Under what conditions we can say W is a subspace from V? Okay, it's really very simple. We say W is said to be a vector subspace of V if I have 3 conditions. The first condition, the origin which belongs to W must be the origin of V. So you don't have 2 origins. So the origin of the subvector space should be the origin of the vector space. The additivity property, which means if you have 2 vectors belongs to W, then their sum is also a part of W. Also, if you the scalar multiplication, so multiplying a number or a constant belongs to the set of real numbers, so you can imagine even the size of W. Okay, the result will still belongs to W. So the 3 conditions already exist. Then vector subspace of a vector space V is a vector space. So once more, vector subspace of a vector space V, a vector subspace of a vector space V is a vector space. And a vector space V is a vector space of V. This is really very important. And we did go through this previously. After those 2 definitions and the applications and the exercises on them in the previous sessions, we went to what's called linear combination. A linear combination, simply, it means I can, from certain vectors, generate another vector. So if I have 2 vectors, let's say 1, 1, 2, 2, I can, from both of them, when I add them together or multiply each one of them with a constant number, then doing the addition, I will have a new vector. This newborn vector can be generated from these 2 vectors. This is what we call a linear combination. So according to the statements, let V be a vector space, then consider we have a set of vectors to be generalized from V1 up to Vm belongs to V. And for certain constants, K1, K2, maybe ones, maybe zeros, maybe numbers, maybe negative, maybe positive, whatever. But they are part of the real set. If we have K1, V1 plus K2, V2 plus K3, V3, and we add them all together, then we can generate a new vector. It is said to be a linear combination of vectors with coefficients. By the idea, the arrangements of K1, K2, Km is critical, and it is a sequence of the coefficients, and V1 and V2 and Vm, they are a set of vectors. Then, after that, we talked about spans. What are the span of a vector space? If we consider V1 up to Vm vectors of a vector space V, then it is really very simple. The set of all linear combination, if I took all the linear combination, all whatever, which covers both the scalar multiplication and the addition property, but it is mixed together. So combining these together, this is the linear combination of a certain vector is called the span. So if I have K1, V1, K2, V2, blah, 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 and such that K1 belongs to R, this is a subvector space from the vector space V. The set of all linear combinations, it's called the span of vectors and denoted as span of V1 up to Vn. This slide is really a very good slide. It contains plenty of definitions. Number one, we know that we can form by using linear combination a certain space. This set of vectors, it's called the span of this vector space. So S is spanned by V1 up to Vm. It means we can get all the vectors in this set, which is S, by a combination, linear combination from these vectors. V1 up to Vm is generators of S. Okay? We can say that these bunch of vectors generate S, or S generated by these vectors. Okay, very good. So V1 to Vn are vectors of a vector space. Then the span is V1 up to Vn and is a vector subspace of V. Now we need to talk about linear independence. And that's a part of our topic today. The linear independence is really very simple. All we have to do is to do a very simple check. For some vectors generate or span a set or apart from a set. Have a set with vectors and we want to discover it's a subset of V. So let V be a vector space. We say that from V1 up to Vn is a subset of or a sub space of V, and it is linearly independent if and only if we have linear combination and the only solution is equal to 0. So K1 V1 plus K2 V2 plus Kn Vn is equal to 0. This will happen only when K1 plus K2, K1, K2, K3 up to Kn all equal to 0. In such a case, it's linearly independent. It's a linearly independent set of factors. Yep. For any span, if we want to know if it is linearly independent or not, simply all we have to do is to get those bunch of vectors, multiply them by the coefficients, and then we will do a homogeneous system. This homogeneous system, as you know from your previous study in matrices, from chapter 1, okay, or from the start of our course, that this homogeneous set of solutions will give you a consistent system forever. Forever, it's a consistent system. But you will be in between consistent, but with just only one solution, or consistent with infinite number of solutions. To be a consistent with a unique number of solutions, it's going to be the trivial solution, K1 up to Kn equal to 0. And if this happens, it's linearly independent. The other case, it's a linearly dependent case, and it will happen if you have a consistent, and this is from the basics because it's a homogeneous, but you have infinite number of solutions. Once more, I will have to remember, in linearly independent case, which you will have a unique solution and the only solution is having from K1 up to Kn equal to 0, the rank of the coefficient matrix should equal to the number of unknowns. This is how you will have a unique solution. This is the only way to reach a reduced echelon form. So if you have this system and you have reduced echelon form, then you will have it's equal to 0. But if you have an echelon form and you can reach the final stage, or the ranks is not equal to the number of variables, it means you can't get an identity matrix, a unit matrix. The unit matrix is the only solution, and it is the only way to get a unique solution. But if you try to solve or work out this system and you didn't end up with having a unit matrix, or the rank is less than the number of variables, then you will have linearly dependent set. What's the linearly dependent set? It means one of the vectors can be generated from the other bunch. Let's say, consider n is greater than 1. So I have more than one vector. Set of n vectors of Rn is linearly dependent. Okay? They will depend on each other. If and only if one of the vector is a linear combination of the others, which means you can find k1, k2, kn, not all of them equal to 0, and it will be, in this case, they will be dependent. To study in particular and to open the light, to shed the light on this fact, I will do those two examples. I want you to check if this set of vectors 1 to 0, 1, 1, and 0, 1, 1 is a subset from R3 or a subvector space from R3. In order to check this bunch of vectors or the set of vectors to be a sub from R3 or a subset from R3, it's really very important. We need to check the system that I told you about. So the first, to do so, we will have to find K1, K2, K3, where K1 times 1, 2, 0, K2 times 1, 1, 0, K3 times 1, 1, the result will equal to 0. So I'm in search at the time being about the right combination of coefficients. Once I use them with those vectors, the result will be a 0. And this is very, very simple. We will have to solve the homogeneous system of equations, as I told you, which are three equations in three unknowns. So it's a k1 times 1 to 0, k2 times 1, 1 and 0, k3 times 1, 1, and it's all equal to 0, which will lead to k1 will be multiplied in 1 plus k2 multiplied in 1 plus k3 multiplied in 1. And if I continue for the second coordinate equation, for the third coordinate equation, those are the three coordinates which will represent a system of equations as you saw. Now I can put this system of equations in an augmented matrix form. If you remark, the elements of K1, which is 1, 2, and 0, they are the coordinates of the first vector. So I would do this system very, very quickly without even thinking about the system of equations, multiplying, equaling to 0. I will write the equation, and I can get this augmented matrix right away. I will take the first vector at the first column, the second vector at the second column, the third vector at the third column. And all of them equal to 0, so the last column will be 0. Now I've put each one of these vectors as column, as you can see. All I have to do is to check the rank between of this augmented matrix or of this matrix. Simply, if you try to come to echelon form or to reduce echelon form, all I have to do is to multiply the first row by -2 and add it on the second row. Very simple. And if you want to continue, it's okay also. Okay, I've continued to reduce the echelon form. The reduced echelon form is a unit matrix, which means the rank is equal to 3. So stop. The rank of the coefficient matrix is equal to the rank of the augmented matrix, of course, because the results are all zeros. And the rank is equal to 3, which is the number of the variables, k1, k2, k3. Those are my coefficients. And the only solution is k1 is equal to 0, k2 is equal to 0, and k3 is equal to 0. And this, my friends, means that this system of vectors are linearly independent. So this is how to discover linear independence between vectors. All I have to do is to take those bunch of vectors, working them out in an augmented matrix, consider every vector as a column, start working your matrix to reach a reduced echelon form or an echelon form. Once you reduced echelon form is a unit matrix, then the ranks will be the same, and the results K1 is equal to K2 is equal to K3 is equal to 0, which means the first, second, third vectors are linearly independent, and also means none of them can be generated from either any one of them or from any other two of them. So I can't generate 1, 1 from these two vectors or 1, 2, 3 from the other vectors and so on. They are completely linearly independent on each other. Okay, the set of vectors B, same way like, I want you to check the linear independence. And it's really also very simple. All I have to do once more is to form the system that we spoke about previously in the previous slide. So I would go for K1, V1, K2, V2, blah, blah, blah. It's equal to 0. And once more, I will multiply K1 by 1 to 0, K2 by double 1 and 0, K3 by 0, 1 and 0, and put them all equal to 0. Now I will have a system of equations. If you remark, that's the first vector, which is the first column, the second vector, which is the second column, and the third vector, which is the third column. Put the equations into a system of equations. Of course, I can get the augmented matrix directly without this step. First vector, first column, second vector, second column, third vector, third column, and it's all equal to zeros. By the idea, maybe I usually feel more comfortable dealing with the augmented matrix, but it's really very simple because the last column is not going to make a difference, so I can just neglect it, but with the understanding that I'm working with an augmented matrix. Now I will try to get to the echelon form. I will multiply the first row by -2 and add it on the second row. This is what I get. The first column, pivot already exists. The second, but if you remark, we missed the last row. So the rank is equal to 2, which is less than the number of variables. And according to our knowledge in matrices, once the number of equations is less than the number of variables, then you will have infinite number of solutions. And the infinite number of solutions is very, very simple. Just to try to expand these rows into equations once more. So it's going to be K1 plus 0 K2 plus K3, which is equal to 0 for the first equation. Then 0 K1, K2, negative K3 equal to 0. That's for the second equation. So doing this, and you will have this system of equations. That's K1 is equal to negative K3, K2 is equal to K3. So it's a linear combination between these coefficients. K1 and K2 depends on the value of K3. So simply, if I choose the K3 to be equal to any number like -1 or something, I will have this combination of coefficients of vectors. So K1 is equal to 1, K2 is equal to -1, and K3 is equal to -1. In such case, that set is a linearly dependent set. Not just only this, but as we will see from the coming slides, the pivot of the first to the last shape of the reduced echelon form. The pivot of the first column already exists, which means the first vector is with us, the linearly independent set of this vector space. And the vector, the pivot of the second column is already exists, but we are missing the pivot of the third column, which means the first two vectors will be the generators of this vector space or this set of this B set. Okay, do K1, K2, 3 once more, the last part. We already solved the system, as you saw, and we already have K1 is equal to 1, -1, and K3 is equal to 1, under the assumption of K3 is equal to -1. This is the combination between vector v1, v2, and v3. And really, if we try to multiply 1 by the first vector, -1 by the second vector, -1 by the third vector, the result will be zeros, which means there is a combination between K1 and K2, not the trivial solution, which means they depend on each other. As I told you, which implies that we can write vector B as a linear combination of the remaining vectors, and we will go through this in details shortly. Now, let V be a vector space. All subset of V with just one non-zero vector is linearly independent. Any, once more. All subset of V, all subsets of V with just one non-zero vector is linearly independent. set of vectors of V which contains the null vector, any set which contains the null vector of V is linearly dependent. Okay, the proposition, the first proposition, which consider V1 is a subset of Rm, and let be the matrix whose column corresponds to V1 as a column, V2 as a column, Vn as a column. The following statements are equivalent. I already told you about this. The set of vectors is linearly independent. It's exactly like telling you that the rank is equal to n, which is the number of variables. Because once more, once you try to solve the homogeneous system of equations, they will you will end up dealing with a set of vectors, okay, with an augmented matrix reaching the reduced echelon form, which is going to be a unit matrix with just only one solution. So those are equivalent to each other. Let's see this example. If I have the set, let the set C, which is 1, 1, 0, 2, 2, 0, 1, 1, 1. Does it linearly independent set? Is this set linearly independent? Once more, how to discover this? All I have to do is to work them out, put them in the equation, which is K1, V1, K2, V2, K3, V3 equal to 0. And try to search for K1, K2, K3. That will make this matrix, this equation correct. So without going to the details of the system of equations, I can directly putting them into the coefficient matrix, which is relative to the rank. So I will take the first column at the first vector at the first column, that's the second, and that's the third one. And I've tried to reach the reduced echelon form. But unfortunately, it is 2, and we have 3 vectors. So the rank is equal to 2, less than the number of variables, which means 2 things. First of all, it's a dependent system of equation. So I'm sorry, of vectors. So this system of vectors is linearly dependent. Not just only this. Also, the vector of the pivot of the first column, okay, the pivot of the first column already exists, which is 1. The pivot of the last column already exists, which is 1. The pivot of the second column is missing, which means also the first column, since the pivot exists, is linearly independent vector. And since the pivot of the third column already exists, then the third is also linearly independent vector. And these 2 vectors can generate the middle vector. So the first and the third are linearly independent, and the middle vector is dependent on one of them. If you give them a good look, you will remark that the second vector is a combination from the first and the last vector, as we would say. All of this were written here. Remark, we have the pivot of the first column and the third column. They are independent, but we are missing the second column vector, which means it depends on the other 2 vectors in generating itself. That's we can find second vector as a combination from K1 times the first plus K2 times the second. And it's really very simple. If you look closely, you will find the second vector is actually the first multiplied by 2 and the 0 times the third vector. And that's the combination that we spoke about. Once more, if I want to go through this quickly, in order to find the set of vectors which are linearly independent out of a general set of vectors, all I have to do is just to put those vectors together in matrix form, taking the first vector at the first, the second column, the third at the third column. Try to work your magic and try to get the rank of this matrix. If I've started with 3 vectors, so if the rank is 3, it means this is a set of independent vectors. But if the set of vectors it's not equal to 3, less than 3, let's say 2 or something, which will mean that this set of vectors depend on each other. And which one of them is a linear combination from the other vectors? It's really very simple. You can get it from the pivots. I will look to the existence of the pivot of the first column, second column, third column. I've discovered that I have two of those columns already, their vectors or their pivots already exist. The first pivot of the vector of the first vector already here, and the pivot of the last vector is already here. So those are the linearly independent vectors, and the second vector is a linear combination from these two. Okay, very good. Now, if n is greater than 1, set, okay, of n vectors, set of n vectors of Rm is linearly dependent if and only if. So a set of vectors are linearly independent if and only if one of the vectors is a linear combination of the others. So in this case, they will be linearly dependent. Let's look at the coming example. And in this example, we are seeking which set of these sets can generate R2. If I look to the first set, and the question is which of these sets generates the vector space R2 more efficiently? Which one of them? So if I took a look for the first set, which is -2 and 1, you will discover something really, very interesting. That this vector, which can be graphed as you can see, I can generate, for example, 0 and 1 from this vector. So A -2 and 1 doesn't generate R2. It's just only one vector and can generate the rest of R2, simply because it is missing some vectors. For example, if this is the main set -2 and 1, and you multiply it by any scalar, you will never be able to get the vector, for example, 0 and 1, or 1 and 0. 0 and 0, you can get it by multiplying -2 and 1 times 0. You can get multiples of these coordinates as vectors belongs to this set, but you can't get 0, 1, 1 and 0. So simply, it will never be generated from -2 and 1. And so span of -1 and 0 doesn't belong to R2, so the set doesn't generate R2. In a similar manner, if we look to C, which have -1 and 1, -2 and 1, double 1, 2, and the -1. This is also it can generate R2, but if you give it a good look, if you try to discuss the dependency of this set, you will find out simply those three vectors, they are linearly dependent on each other. And if you give a good look, you will find that the third vector can be easily got from the first vector simply by multiplying by -1. This is obvious in this case, but in general, I would put them in a matrix form and searching for the linear independence. It is easy to identify that except linearly dependent vectors, that's one of them is a linear combinations of the other, and I've explained the reason. If we go to the third set, which is the B1, which is -2 and 1, 1 and 1. If you look closely to this set, you will discover that I can generate most of the vectors in R2 from these two vectors by choosing different values for K1 and K2. And also they are linearly independent. There is no factor or there is no scalar value. You will multiply in any one of them and you will generate the other vector. So B could be a basis of R2. So it is easy to prove that all vectors can be formed as linear combination of the set, making it generator of R2. The summary of the previous three problems. Number one, the first set of vectors, it can't generate R2 because it's missing some of the vectors. The second set, okay, it can span R2, but unfortunately they depend on each other. The third set, okay, it is the optimal one, linearly independent, and also can generate R2. Now I will talk about basis and dimensions. Basis and dimensions. I want to put rules, okay, to have a basis for any subvector space. And it's very, very simple. From the definition, let V be a vector space, and the beta is a subset from V. We say that B forms a basis for V if beta is simultaneously, if this subvector or if this set satisfies main two conditions. Number one, a generating set of V. Number two, linearly independent. So those are the main two conditions that we should have in order to have a basis for a certain vector space. Number one, the generating set. Number one, the generating set is linearly independent. Number two, it can generate all the vectors in the set. If a set forms a basis for a vector space, the order in which we consider the vectors in the set is relevant. And this is really very important. The order is important. So would go the set for this example, and it's a very quick example, but it's very active, like the three that we had, and we will apply our rule. Let's discover this. Okay, does the set -2 and 1 and 1 and 1 form a basis for R2? Does it form a basis of R2? This is very, very simple. I can check this simply by doing the two steps. Number one, checking the linear independence. Number two, if it is generating set. And they are connected and very easy to check. We will need to check first the main two conditions, the independence and the generation. The independence, it means take this system of equations and search for K1 and K2, which will satisfy the equation as you know. So check the rank of the vectors matrix, K1, V1, K2, V2 is equal to 0 and 0. That's the coefficient matrix. We'll take the first vector at the first column, the second vector at the second column, and I will try to get the rank of this matrix simply by trying to get to reduce the echelon form. It's very, very simple. Yes, we can get to reduce the echelon form or an echelon form, as you can see, which means the rank is 2. That's K1 and K2 must equal to 0 in order to make K1, K2, V2 equal to zeros. So they are linearly independent. Condition number one, check. I will go for condition number two, which is, does it generate R2? And also it's very, very simple to check. We'll solve the system x equal to b, where b is any vector a and b belongs to R. Very simple. I will put them in an augmented matrix form. That's my coefficient matrix, and that's a and b. And by logic, the rank of the coefficient matrix is equal to 2, which means it will force this system to have a unique solution, which that's this set is a generating set for R2, which means the two conditions are satisfied. Rank of A equal to rank of A and B, all of them equal to 2. The system is always consistent, which means it can generate R2 simply. Since the two steps are done, then B forms a basis for R2. In a similar manner, let's do the same with this set, but those are vectors in R3. And I want to check if they form a basis for R3 or not. Very simple. What I have to do, we will need to check first the main two conditions, the independence, then the generating set of vectors. For the independence, let's consider the main matrix, whose columns are vectors of R, of beta. So that's the main matrix whose its columns are vectors of beta. Then I will check the rank of this matrix. I will take the first vector to be the first column, the second vector at the second one, and the third vector at the third column. If you try to look closely, you will find out this matrix is with a rank out of 3, which means it's a 3 by 3 matrix, leading to just only one linearly independent system of equations. And the vectors are linearly independent. It's a unique solution, and it's a linearly independent set of vectors, I'm sorry. Now let's consider if I have ABC, since this is a linearly independent system, so the coefficient matrix, it's in all times will be with 3. So also the augmented matrix will be with order 3. So possibly it will give you a generating set. So once more, let's do the generation. finding any vector whatsoever, ABC, which can be formed from the three linearly independent set of vectors, K1, V1, V2, V3. So putting them into a matrix 4 and trying to solve it, the only solution is going to be a unique solution, which means I can find K1, K2, K3, which generate any vector belongs to R3, which means that it is a basis for R3. Once more, to have a basis for any vector space, I should check two things: the linear independence, and number two, the ability to generate any vector belongs to this vector space. Once more, the set is a subset from R3, forms a basis for R3. Does this set forms a basis for R3? It's very, very simple. Now we can say that B is linearly independent from this set of vectors. That's really to prove. Number B generating is R3. That's the summation of the previous problem. Both of them are already exist, so it forms a basis for R3. The coming proposition is about a linearly independent set of n vectors forms a basis of Rn. So a linearly independent set of n, that's the bottom line that we discovered from the previous problems. Theorem. Let V be a vector space. If B and C are bases of V, then B and C have the same cardinality. They have the same reliability. They are the same cardinality if they are both of them bases for this vector space. Dimension is the number of the vectors in the basis. So the dimension of a vector space, dimensional vector space, dim V, the number of vectors in a basis of V. يبقى تاني once more, the dimension of a vector space, it is the number of vectors that can generate it or in the basis of V. Position, let V be a vector space, and you have U and W. Both of them are subsets from V, the two vector spaces of V. If the dimension of U is equal to the dimension of V, then U is a subset of W, and if U is a subset of W, and U is equal to W. Convention of this, let be a vector space. By convention, we say that empty set is a basis for the null set, and the dimension is equal to 0. That's a very good statement, and we may need it in the multiple choice questions, so you should go through it more than once. Okay, so according to this, we can say that's for the set of vectors form a basis of R2. And the number of vectors, as you can see, it's 2. So the dimension of R2 is 2. For those set of vectors that we already discussed previously in the previous example, they are basis for R3. The dimension of R3 is 3. And also for this matrix, which is 3 by 2, those are the generating matrices or the basis for this matrix. And simply the dimension of a matrix is going to equal to the multiplication of its rows and its columns. So if I have 3 by 2, the dimension of this matrix is going to be 6. Okay, to confirm all of this, these remarks are for this. For the dimension of Rn is equal to n. The dimension of any matrix, okay, of m by n is going to be m times n. The standard basis for every vector space, it's going to be the canonical form that we will announce. For, let's go through it. It's going to be the basis of Rn, which is formed by vectors E1. For all I belongs to 1 and n, E of I, or the this set, it will, or each vector will consist from all the elements equal to 0, except its pivot. What I mean, if we are in the R1, the dimension or the basis, it's going to be just only a set containing 1, because the dimension is equal to 1. If I am in R2, so the main basis is 1 and 0, 0 and 1. And it's the standard basis of R2. In R3, it's going to be 1 triple 0, 0 1 0, double 0 and 1. which is the standard basis for R3. Also, the standard bases are called canonical basis of Rn. By this slide, we come to the end of our slides for basis. All you have to do is just go to our gym. So once more, all you have to do is doing more exercises, and always remember practice makes perfection. So do some problems, please. From the exercise, you don't have to search for a lot. From the exercise, you will find a bunch of problems satisfying every corner and aspect of our lecture today and the previous lectures. Here he is asking you, let S be the set 1, 2, 3 vectors. Verify whether S is linearly dependent or linearly independent, which is an easy task to do. All we have to do is to check K1, V1, K2, V2, K3, V3 equal to 0. So I would take the first multiplied by K1, the second by K2, the third by K3. Or simply, I can form the matrix, which its columns are the vectors, vector number 1 for the first column, vector number 2 for the second column, vector number 3 for the third column, as you can see. To discuss the independency, all I have to do is to get the rank of this matrix. On a matrix form, that's the shape. And by elimination, solving this system by elimination or by Gauss or whatever, this is what you get. This is the coefficient matrix. That's the system once more. And simply, I will get the rank. If you try to reach the echelon form, you will, or the reduced echelon form, you will reach this case. Multiplying, just adding the first row and the second row, multiplying the first row by 93 and add on the last row. And you will be able, in a couple of steps, to reach this matrix. Of course, by a look to this matrix, the rank is equal to 2. So by linear independence, this matrix or this set of vectors, they depend on each other, or they are linearly dependent. So either one of them is dependent on the other vectors in generation. And this is really very simple. If you remark once more, the pivot of the first column already exists. So that's vector in my basis. The pivot of the second column already exists, so the second is okay. The third one is missing its pivot, which is supposed to be here. So 1, 2, 9, it's a linear combination from these two vectors. Okay, if I want to find this linear combination, all I have to do is first to get the K1, K2, and K3. And of course, K1, K2, K3, they are not equal to zeros. It's not the trivial solution. They depend on each other. So simply K1 will equal to half K3, K2 will equal to negative 3 over 2. That's K1 and that's K2. And considering K3 is equal to T, as we are solving an infinite system of equations, so K1 will be half of T, K2 will be negative 3 over 2 of T, and K3 will be equal to T. Take T over 2 as a common, as a common. So you will have T over 2, 1, negative 3, and 2, as you can see. If I consider T is equal to 2 for simplicity, then the coefficients of this combination will be 1, negative 3, and 1. Okay, this is very, very simple, as you can see. Of course, the results already exist here. For the second, he asks you if R3 that doesn't belong to, get a vector of R3 that doesn't belong to this span. Okay, we need to find something, okay, like, let's say 0, 0, and 1. Vector 0, 0, and 1 doesn't belong to the set. So once more, it's described here. This is the general solution. So they are linearly independent. The pivots already exist. And so the generating set is going to be the first and second vectors. Those are the coefficients once you consider k is equal to 2. And they came from this equation. Simply, if you remark, those are the pivots of the first and the second column. So those are the basis for this set. And there are two pivots, as I told you, they are linearly independent, blah, blah, blah. So V1 and V2 are the linearly independent sets. From them, I can generate V3. If you want to know how to get the V3 out of V1 and V2, just get V3 on one side from this equation, which means V3 will equal to V1 over 2 minus 3 over 2 V2, and that's the case that you can take. Okay, which means really, if you multiply V1 by negative half and the V2 by 3 over 2, you will end up having V3 as this. To come to the question, second question, he's asking you whether these set of vectors or of A are linearly independent or not, which is خلاص, it's very simple. B is true that span A equal to span B. We will see about this. For the first part, all I have to do is to take the vectors of the first set, putting them into columns, and try to search for the rank for this matrix. Okay, and that's the second set. So if I took the first set and tried to solve the linear system by, as we already know, the result will be that's 1 in the first vector and the pivot of the second vector missing 2 vectors. So actually, this set, which is set A, is a linear combine. It's linearly dependent, and one of them can be formed from the other 2 vectors. I believe, according to the pivot, that the first pivot or the pivot of the first column already exists. So the linearly independent set will be, or the basis will be, 4, negative 2, and 8, and 2, 3, 0, 6 for this basis, this set, I'm sorry, and 1, 4, negative 5, and 8 can be generated from these 2 vectors. The first column and first have pivots, so that's the set we are searching for. Span of A is 2, span of V is 2, so they're supposed to equal to each other. We check each column of V lies in the span of A. If we want to do number B, it's very, very simple. If we want to check if span of B is in the span of A, I will have to check that each column from the columns of vectors of matrix B is already a linear combination from the set of vectors in matrix A. And this is also very simple to do. I can take this matrix, although of course I know that the third column is a linear combination, so I can neglect it, but I will keep it with you just to stress on this fact. I've taken the first set, which contains these 3 vectors, and I've taken the first vector as B as apart from the system Ax equal to B, as we saw in the previous slide. I will try to solve this augmented matrix. First step, I've adjusted the first column, then I will adjust the second column, as you can see, and voila, we reached the top, or we reached the reduced echelon form, which means that K1 will equal to K1 will equal to the value of K4, and same way like for K2, it will equal to, as you can see, negative 1 minus 2 positive 2 times K3, as you can see, that's for K1 and K2. K3 is already equal to 0. That's the value of K1 is equal to 1, K2 is equal to negative 1, and K3 is equal to 3. I'm sorry, to 0. So if I choose the K3 is equal to 0, these are the values that I will use. If you remark, this is 1V1, negative 1V2, 0 times V3, and it will form B1. So actually, the first column from the set of beta is from the set of beta is a linear combination from the set of vectors in A. In a similar manner, I will solve the coefficient matrix, but with the second column of matrix B. In a similar, exactly the same way like, I will be able also to get K1 as a function K3 and K2 as a function K3, inserting K3 equal to 0. So the linear combination will be K1 negative 7 over 2 and K2 is equal to 5. Bottom line, also the second column is a linear combination from all the set. So it is true that the span of A, okay, span of A is equal to span of A. You have here this example also, 7.3, which gives you E, it's a set with two vectors, and the F is a set also of two vectors, okay? And I want to check and find the basis, find the dimension and the basis for E plus F or for E intersection F. First of all, let's look to E and F. E consists of two vectors and F consists of other two vectors. The dimension, the first two vectors are linearly independent, and also the second, and they are linearly independent, of course. The dimensions, the dimension of the first set is 2, and the dimension of the second set is 2. So now I have the dimension. If I want to get the dimension and the basis for E plus F, all I have to do is to stack the four vectors, put them all together in a matrix form. So that's the first column, second, third, and fourth, which are the sum of the vectors in E and F. I will try to reach a reduced echelon form. Doing the steps, this is step number 1, and that's step number 2. I'm seeking, as I told you, the rank. The rank is equal to 3, which means I have three vectors. Out of all those vectors are actually form the basis, and the fourth will be a linear combination from these vectors. I can find the pivot of the first column, the pivot of the second column, the pivot of the third column, which means that the first two plus the first vector from F, those are the basis for the addition. 111, 1221, 01, -1. And the vector 112 is a linear combination from these vectors. If I want to go through the intersection, it's very, very simple. All I have to do is to solve AV1, BV2 equal to CW1, DW2. So actually, we will check vectors X that lie in both E and F, which is the meaning of the intersection, that you have a vector belongs to both sets. We will find scalars A, B, C, and D. If you try to solve this system, it's very, very simple. All I have to do is to move these two guys to the left-hand side. So just move them to the left-hand side. I will have an equation V1 BV2 minus CW1 minus DW2 equal to 0. Now, this equation is an augmented matrix, okay, and can be put easily on system of equations. That's the system that I will solve in order to find what are the linearly independent set that exist. Okay, so working them out, we will find that the vectors of A is equal to can be solved, as I told you, continue for the reduced echelon form. That's A is equal to negative half of D, and B negative half D is equal to 0, and K3 or the C value is equal to negative half of D, which means A is equal negative half D, B negative half D, C negative half D. I can choose D as 2, and then the values will be 1, 1, 1, and 2. This is the values of K1 up to K2 that will make those vectors actually exist. Then the values will be E1 equal 1, B1 1, C1 and 2, and the vectors E intersecting F will be 2, 3, 3. That's the vector that we can find easily. That's the vector of the intersection. Okay. Another problem here, you are giving A and you are giving B. Both of them are sets of R3 with a specific information. For the first one, the three coordinates equal to each other. For the second set, you have y is equal to 2x, z is equal to x. So I can get actually the basis and dimension for each one of them. The first, I will use the condition, replacing x, y, and z by t, and taking t as a common belongs to r. So the generating vector is triple 1, and the basis one dimension. The basis, the dimension of this basis is 1. Same also goes for the second set. We will replace x I will leave x, but I replace y by 2x, z by x, and then I will take x as a common. I will have the vector 1, 2, 1, which is generating for these bases. And so the basis is 1, 2, 1, and the dimension is equal to 1. Now, let's check A plus B. I will stack them together in one system, as we did previously, and I will try to solve for finding alpha and beta. If we did so, we will reach a unique solution, which means they are linearly independent set of vectors, that A plus B will be the first vector plus the second vector, so it's going to be the dimension 2. For the intersection between them, we will do exactly the same. A times V1, which belongs to the first set, and the B times W1, which belongs to the second set, and they both equal to each other, making me solving AV1 minus BW1 equal to 0, which means I can simply solve this system, and I will end up having the trivial solution that K1 is equal to 0, B is equal to 0, so the only intersection between them is the origin, as you can see. And the dimension is 0. Same way, like, I'm really very sorry for having this long session. I know we had a lot of information, but also we did solve some exercises. The rest of the exercises, you will find them if we get time. We will go through some of them in campus, inshallah. Thank you very much for listening to this video. I've sent already the PDF for all of you previously in order to make your life easier reviewing the PDF and with combining it with the lecture to make it very easy for you. Thank you very much, and thank you for your time. Please try to resolve all the problems that we did go through, and try to do the quizzes regularly in order to be more close to the problems that you will may face in in your exam, inshallah. Thank you very much. I'm very, very happy with you, and I wish you all the best. Thank you.